Hi, I'm Frank Farris from Santa Clara University, and I hope to interest you in my Bridges paper, Wallpaper Chainmail from Non-Planar Rings. Of course, you can read the paper, but I thought nothing would catch attention like a live demonstration of some of the actual chainmail. This has been 3D printed. I find it very beautiful. If you look down upon it, it does appear to exhibit wallpaper symmetry, but all the chainmail that I have ever seen before is made from circular rings, or at least from planar rings. And you see that these rings are more like pentagons, and if you lift them up, you see that they wiggle up and down. And it's that up and down wiggling that allows them to link with each other in really interesting ways and create some great patterns. And furthermore, it's just great that when you pick them up, this allows them to fall in really interesting ways. This one develops quite a lot of curvature on both sides, so it's a very flexible kind of chainmail. Here are two more. And from a mathematical point of view, if you look straight down upon them, they exhibit the same kind of wallpaper symmetry. This is that P3M1 symmetry pattern that looks like linked curvilinear equilateral triangles. So it has threefold symmetry and certain mirror symmetries. But in fact, these two chainmails are strikingly different from one another. Here, the design seems to indicate that there is a vertical mirror symmetry with the left and right sides of that equilateral triangle being the same. But if you look more closely, you can see that where it goes up on one side, it goes down on the other side, up on one side, down on the other. And I call that a flip symmetry, meaning that that triangle falls into coincidence with itself when you turn it upside down around an axis that looks like the mirror axis of that triangle. Now let's see what happens when we pick this one up. It falls into a pattern with a fair amount of curvature, not as much as the previous one, and as you might suspect, when I flip it onto the other side, it exhibits really the same amount of curvature on that side as well, and that goes with the idea of the flip symmetry. This is a very different kind of pattern, although it looks the same. It looks like it has the same symmetry type as the other when you look from above. Here, each ring really does have mirror symmetry. So that's a pretty good view, that where it goes down on the right, it also goes down on the left. So it's mirror symmetric about that axis. And let's see what happens when we pick it up. From this side, it remains quite flat, but when I turn it over, it falls into this shape with really quite a lot of curvature. So I think that's a very interesting material. And I invite you to read my paper where there's all the details about how to make these for yourself. Nothing would delight me more to know that there was someone out there making chainmail according to the recipes that I outline in my paper. I wanted to say a word while we have this camera going about where this project came from. A year ago, I was working with Santa Clara student Wilder Boyden on a project to discover types of woven polyhedral shapes. So shapes made from bands that exhibit polyhedral symmetry. And this is one of them. And I think that this pattern might be familiar to people. It's kind of well known how to make this from 10 strips of paper with origami. Each band here has threefold rotational symmetry and mirror symmetry. So it's not that this is such an unusual thing to be able to construct. But the thing that Wilder and I did in our paper was to explain a large function space that includes all possible things of this type that are woven from bands while retaining polyhedral symmetry. Both of these objects are for sale at Shapeways, and I invite you to check them out. So from a project about weaving bands to make polyhedral symmetry, you can see that maybe it wasn't too much of a leap to think about weaving bands in order to make chainmail. Now, give me a minute here to shift over to some PowerPoint slides, because I'd like to just show you a little bit about the history of this project and take you through some of the details. So Here's one of the pattern examples. That's actually one of my favorite ones. That's a two-color pattern indicating twofold symmetry in chainmail. This all started when I spent the fall at ICERM, the Institute for Computational and Experimental Research in Mathematics at Brown University in Providence, Rhode Island. They gathered many of us together for a beautiful semester program called Illustrating Mathematics. This is the view from the coffee room at ICERM. That's the First Unitarian Church and the Science Library at Brown up on the hill. Beautiful location. When you give a lecture at ICERM, you see this view with the Rhode Island State Supreme Court out the back window. Glenn Whitney led us in an installation project. It was really a magnificent semester, but one of the most important things I learned there was learning about Grasshopper as a plug-in to Rhino. Many people know Rhino as a program for architects. Architects can use this to design all kinds of interesting buildings, and really there are lots of different kinds of designers that use Rhino. But when it's combined with this Grasshopper plugin, it becomes rather the ideal thing for a mathematician who wants to make stuff in the real world. These boxes here are components, and for instance, this component contains a formula that will determine the x-coordinate of this, a single one of these rings. And then these controls here control parameters. So you can slide those parameters and see your design updated in this Rhino window over here. And it's just a wonderful tool to look for beautiful designs. Just for instance, here is the formula for that particular chainmail with threefold rotational symmetry. And you can just maybe see barely that there in the X out box is a way to encode the X value of this parametrized curve. So anyway, the most important thing that I learned at ICERM was how to use Grasshopper. The first thing I did was to go back to a very old project. Way back in 1999, I wrote a paper with Hans Christian Rossing about woven rope friezes. So it was pretty easy to make a design here that looks like it's made out of steel, but it does have a certain frieze symmetry to it. And then, of course, you can put a bunch of friezes together and they link magically like this to make a wallpaper pattern. So that's where I was in my early experiments. And then we had Computational Textiles Week at ICERM. And I learned about mathematical theories about knitting, and it was pretty easy to implement those to make a stockinette stitch and a ribbing stitch out of knit. And then, of course, I started making those into cylinders and other kinds of shapes, more on that later. But I gave a file similar to this one to the wonderful ceramic artist Timia Tihanyi, and she used her 3D ceramic printer to make an object like this. This is work still in progress with the two of us, and I'm very excited about the future of that project. But back to chainmail. After Computational Textiles Week, someone was talking about chainmail, and I realized that I had all the tools to start making some. So this does have wallpaper symmetry when you look at it in a two-dimensional projection. And here is that other one. I don't know if you can tell that the one on the right is the one with actual mirror symmetry because the crossings go over when rings cross, whereas this one, the crossings go over-under, showing that that is the one on the left that has flip symmetry. My initial project was to make wallpapers with each of the 17 wallpaper types, but then I realized that I'm actually not talking about wallpaper symmetry, but about the symmetry of the layer groups in 3D. So for instance, here are two patterns that both, if you look straight down on them, you would say that they have that pattern type that only has twofold rotational symmetry and no other symmetry. But on the left, that symmetry is implemented as an actual mirror symmetry on the, sorry, that was on the left, yes. And on the right, it's implemented as a flip symmetry. So I'm not positive exactly how many of the 80 layer symmetry types can be implemented in chainmail. So, but I think that they all can. So after making chainmail, I put it on surfaces. Here's the upper hemisphere of a sphere made out of chainmail. Here is the pseudosphere made from chainmail. These have not been realized in the real world, just in the imaginary world of Grasshopper. And then I also was working a little bit with John Edmark on blooms, his bloom project. And so I made a chainmail blooming Fibonacci spiral. So this, he and I are theoretically working on a paper to explain the mathematics behind this. It's exceedingly beautiful. So I hope this gives you a taste of what I'm onto with mathematical chainmail, and I hope that you'll enjoy reading my paper. Thanks for listening.